and began to work in the area of range frequency theory. Alan, of course, was a wonderful and very dynamic lecturer, very exciting. He won awards for his teaching. He was extremely clever and able to negotiate difficult situations. He was able to introduce a criticism of someone's research in the most subtle way. And many people didn't even realize that a devastating criticism had been given by his attitude in which he gave these comments. When I left UCLA, so he was great as a graduate mentor. I had complete freedom to work on whatever I wanted to work on. And I was encouraged, had a lot of opportunities to talk with him and discuss the various issues that I was thinking about. He gave a lot of good help with writing, although his handwriting, he wrote very tiny and constipated writing suggestions that were difficult to read, something that caused Barbara Tabachnik, one of his former students, to have nightmares. But when I left as a graduate student, finished my degree, I told him that he had ruined my life because it was the best time as a grad student. And I would never be happy again. If you understand the theory, you understand why he was happy to hear that. All right. Well, you heard Eddie talk about the frequency effect. See if I can see that. And here's the ranking -1, and the range effect is simply the position, you heard Victor talk about that, the position of the stimulus related to the two endpoints. So in range frequency theory, the idea is that a response to a stimulus, and originally it's proposed in the area of category judgments, but in many experiments we've found it applies to magnitude estimations and all sorts of things you might describe as cross-modality matches. When you get a numerical response to a stimulus, you've got to realize that its value is not just a function of the stimulus. The basic idea is the behavior is not a function of the stimulus, and so one of the problems to explain is that behavior is not a function of the stimulus. Many theories begin with the response as some function of the stimulus, but it's not. The context is also involved, and here's a description of a theory in which the idea is a compromise between two competing theories. Although they're correlated with each other, they're mathematically independent, although statistically dependent. And so recently I did a lot of work in this field back in the 70s, 50 years ago. But in recent years, and I was working on many other topics over the years, I kind of came back to problems in contextual effects by some articles that appeared in the JEP General on happiness that people have with their salaries. And as you may be aware, there's many attempts to reinvent the wheel, perhaps based on the idea that people aren't aware of the wheel having already been invented. And together with Julien Rouvere, who's co-author of my talk here, we set out to do some research simply to test the new theories that have been proposed, included some of the older theories, and that was published in JDM last year, 23, and I want to tell you a highlight or two from that study, and also one that is currently in the works and has just been submitted. So among the various theories, of course, there was Helson's theory of adaptation level, a theory that got renamed anchoring and insufficient adjustment without any reference to Helson, that people then believe that's the beginning of the research on anchoring, but there was a lot of work in anchoring in the 30s and the 40s, and the theory of anchoring and adjustment with insufficient adjustment was already in Helson 1947. And Victor described some of his early work in the 60s on anchoring effects. There's the correlation regression theory, decision by sampling, and of course Parducci's range frequency theory. I'm going to illustrate the predictions of range frequency theory with a simplified prior version that just says that we're going to let the psychophysical function, and in the case of the utility of money, it'll be notated, and you saw already on the slide, U of X, which you could think of as a psychophysical function or a utility function. The weight of the range and frequency principles will be set to 1/2, and we'll let the utility function be the identity function. And here's some predictions of range frequency theory on the left of that simplified range frequency theory. And here we've got two curves that cross over twice. And curves that cross twice produce a critical test of theories that require the curves don't cross, or that they can cross only once. And you might be asking, well, how do you get curves to cross twice? And the answer is that you use cubic distributions, or in this case a finite approximation to a cubic density function, because that'll produce something that looks like the integral of a cubic, namely a quadratic function. And so I used a cubic kind of like the one that I had used in 1974, 50 years ago. And the dashed line, the open circles, shows the predictions for a density function in which there are 5, in addition to the 7 points you see there that are common to the two distributions. There are 5 additional salaries, like $41,100 and $41,800. There are additional values between 40 and 42,000. And then between 46 and 50,000, there are another 10 values inserted in there, producing a context. And the subject's task was simply say, how happy would you be with these salaries, given you're in a situation where this is a set of people who are equally trained, equally experienced, equally productive, and equally meritorious for their salaries as you are. And how happy would you be with each of these salaries in this occupation? And you see that the happiness increases with salary, but it's steepest in the region between 40 and 42, where there are additional contextual stimuli have been placed in that condition, and in the region between 46 and 50. And the other distribution is the opposite for the other curve. The solid curve with solid points is the opposite cubic density function. And in that case, there have been additional stimuli here between 42 and 46, and it's steeper in that region between 50 and 52. And over here we have a web-recruited sample that included some people that worked full-time and some people that were not working full-time, about 250 people in the experiment. And you see the curves cross in the way that they're expected to do by range frequency theory. And the open circle is significantly greater than the solid point, the means, and significantly less at 46 and significantly greater at 50. And you calculate the psi value for that, you'd be convinced it's a reliable effect. Here we divided the sample for those that work 35 hours or more into the people that earned more than 52,000, which is greater than the most that we used in the study, or those that earned less than 52. And those people that we get the same effect of the experimental manipulation in both groups. But you see that people who earn more than 52,000, they didn't like these salaries. They rated them much lower than the people that earn less than 52,000. So there's an effect of the background, and this is something that Harry Helson had talked about, that people bring a context with them when they come into the experiment, and we're able to use the range frequency theory and approximate by a beta distribution the prior context that people earning different incomes bring with them, and it influences the judgments as well. Now, within and between subject experiments, produce different kinds of results. And this is one of the reasons for this crisis of replicability, that people do experiments one way, they do it another way, and you get different results. And those of us that understand something about contextual theory understand and are able to predict strange results. So I published one in '99 where we randomly assigned people to conditions and asked one group to rate the number 9, how big is it, and another group to rate the number 221, how big is it? And we found that the number 9 is significantly greater than the number 221. And it's a good, strong effect. If you understand something about contextual theory, you understand why many of these results in between subject designs as published in social psychology produce these results. So we're interested, what happens if you manipulate the context within subjects? Part of the problem with manipulating context within subject is that a positive and a negatively skewed distribution combine, and if they mix together, you get something that's closer to uniform, or with those two cubics that are opposite, they sort of cancel each other out. But if there's an identifying variable that creates a separation of contexts, people can handle different distributions. So people understand questions such as a small elephant and a large mouse, which is bigger. And people can handle there being the sizes of elephants and the sizes of mice and the sizes of animals. They can handle different kinds of contexts which have set and subset relations to each other. And we thought people can understand the idea of different workplaces that have different distributions of salaries. And so the work that's currently in the works or had been submitted for publication, we had different job places where there are different distributions of salaries within them. Here are two of the trials to kind of illustrate the basic idea. So how happy would you be if you earned your salary at $50,000 and there are two other people who are equal to you and hired at the same time and are equally deserving of salary, who earn $40,000 and $72,000. And another trial is your salary is $46,000, and the others have this positively skewed distribution. There are now 7 others, and they have a positively skewed distribution ranging from $40,000 to $52,000. So there's a different range in the second case, in this one numbered item 21. And according to that prior range frequency theory with U of x equal x and weight being a half, you could predict that people would say they'll be happier at $46,000 than at $50,000. And in fact, that's what works out. According to the first idea that we had, is that the compromise between the context you bring with you and the context that you bring in the experiment is like the context that happens from the whole experiment, which is sort of like what Helson called the background, and the context that's been manipulated within the trial. So you just apply range frequency theory to the entire experiment, in other words, all the salaries that have been presented, and apply it to the context within the trial, and we use 1/2 as our weighting of the two and said, okay, then the prediction will be 1/2 of each of those. So that's the prior model of that. And there's a series of experiments. I'll just describe briefly one of them that happens to be numbered experiment 3. Assuming this thing makes its way to publication, you'll recognize it then. And indeed, the ratings can be higher for lower salaries if they're put in the appropriate context. So for example, if there's just one other person, 42,000 is rated higher if the other person earns 40. In other words, you're paid more than there are 2 people in the context within that trial. About a category greater than the rating of 50,000 when the other person earns 52, so now you're paid the less of the 2 people. And the T there is 8.45, and we can work out the reliability. Another way of estimating the magnitude of the effect within subjects is what percentage of the subjects show that phenomenon. And about 147 of the 215, about 68%, give a higher mean rating to 42 in this case than to the rating of 50,000. And this result is within subjects. So it's a little more noteworthy than just saying that 9 is a bigger number than 221, because if you put them together within subjects, everybody except the person that isn't reading it judges the 221 to be bigger. So here's a positive and a negative skew, prediction on the left of the prior model and the data on the right. Here's the effect of manipulating the two endpoints independently. You can manipulate the lowest value in the context and the highest value in the context. This experiment is holding the value of your salary is 42, 46, or 50,000 in a context of two other people who either earn 20 and 52 or 20 and 72. So that's manipulating the upper value, or 40 and 52 or 40 and 72, manipulating the upper value. And so if both are shifted, it pushes the whole curve down. And so that's like, there are some experiments where people move the whole range of stimuli up and notice that the curve tends to shift down. But you can also take the two end values and move them out. That creates a greater range and produces a lower slope. That's the curve that's in the middle. Or you can push them in, creating a smaller range, and that creates a steeper slope. That's the red line with the dashed red line that's shown on there. And you'll see that the relation of the heights of the curves and the slopes are also observed in this within subject version of the experiment. And these manipulations of range, holding the rank constant, rule out things like decision by sampling and things that are based strictly on the rank. And the other, the manipulation where you saw the curves crossing flight, they rule out things like Helson and Johnson and Mullally theory and the various theories that require that things can only cross once. Now there was an effect that we discovered within subjects that was not predicted by the within subjects range frequency theory that I showed you. When you're paid the least, or you're paid less than the other when there's one other person, the dissatisfaction or satisfaction depends on what the other person is paid. And that's not predicted to happen. And we think that this only could have been observed in a within subject experiment because the position relative to the endpoints in a between subjects design, since the endpoints are fixed and there's simply a single distribution, that position is isomorphic to how much less you're paid than the most. But when the most and the least vary, then that becomes not statistically independent, but in the mathematics terms, it becomes independent of the range term. And so a new distribution is created. And so we revised the model to include a range frequency analysis of the total distribution, of the within trial distribution, and of the inequity distribution, and simply took the average of that as our prediction, and that seems to reproduce the effect. Here we got, I was griping to some of the grad students during the break that PowerPoint has a tendency to change your slides around. At any rate, there should be a curve coming up here in the lower, which is what your rating would be by the model, depending on where there's just one other person. As your salary increases from 42 to 50, if it's a between subject experiment, those slopes should go to 0. But what counts is whether you're most or least. So if you're the least paid person, your rating should be simply 1 out of a 1 to 7 scale. And if you're the most paid person, the rating should be 7 because both the range and the frequency value are at 0 and 1. In the within subjects experiment, the between trials context produces those positive slopes for the predictions. And notice notice that what the other person earns, if you're paid the most, has no effect. And what you're paid, if you're paid the least, what the other person is paid has no effect. But if the value switches from being the least to the most, it makes a big difference. And if you look at the data on the right here, you'll see that at the upper end, it's fine. It's exactly, well, fine in the sense of it is in agreement with the theory pretty well. In other words, notice that the red curve comes up and joins the other curve, and that the three values at the upper end on the right all pretty close coincide. But at the bottom end, it matters how much you are below the increased value. And here's the revision of the model on the left and on the right, and that seems to be able to describe the result. So basically what we did is manipulate the endpoints, the range, and the frequency, holding the other constant. We found that the model that was proposed did a medium good job of predicting the results, but we're not happy with the 0.88 correlation with the data. We like to get 0.98 or better correlation, and so we can do that by bringing in the distribution by actually estimating parameters, of course, rather than just using prior values. And this revised model was able to describe that effect. So with that, I'll say thanks very much for your attention.